Let's look at this example on arc length. So we just derived, or the previous video derives the formula for arc length in 6.3. So if f of x is equal to 3x to the 2/3 minus 10, find s, or arc length, from 8.2 to 27.17. You may want to check to make sure, I mean, these points need to be on the curve, but essentially you're saying x is 8 and x is 27. So our AB is 8 to 27. So to apply the formula, it's just right there. We know we're going to need f prime. So let's just take f prime. So f prime of x equal to 3 times the 2/3. So it's going to be, oh, actually I wrote this one all out, didn't I? So 3 times, and then it's 3. Wait, what did I just do? Oh. So here's 2/3 times the 3, and then subtract 1. So it's 2/3 minus 3/3. So you end up getting 2 over x to the 1/3. All right, so next thing what I did is I went ahead and substitute into the integrand, just to do a little simplification first. And so it's 1 plus 2 over x to the 1/3 and that's quantity squared. So that's f prime, right? That is f prime. Okay. Simplify that, and you get this square root of 1 plus 4 over x to the 2/3. No, let's just keep going. Okay, so over here, I was going to bring it down, but that's okay. Let's do it down here. So continue to simplify that to a form that we want to try to integrate. So let's add it up together. So that's going to be x to the 2/3 plus 4 over x to the 2/3. This goes all the way down like that. Okay. And let's do the square root. So basically what I'm going to do next is the square root of x to the 2/3, which is x to the 2/3 to the 1/2. So it's x to the 1/3. We don't have to worry about it being negative or using absolute values or anything because we are positive over here. Okay, I don't want that in my work. Okay, so you get the square root of, let's try to do a little better. Sort of a blessing and a curse to use the iPad because I want it to look nice because I can move stuff around. But then again, I can move stuff around and make it look nice. If it was pencil, I'd just kind of keep going probably. So then, where was that? Sorry, so square root of the numerator. And so that's x to the 2/3 plus 4 all over x to the 1/3. Okay, so now that's something we can try to integrate. So we're going to integrate that from, and what's our limits of integration? not that. It's right there. 8 to 27. So x goes 8 to 27 of all of the integrand. So you may do all this inside the radical, the integral, but you'd have to bring it all the way through. Sometimes it's nice to do this to the side and simplify your integral, especially when you know it's going to be kind of messy. So x to the 2/3 plus 4 over x to the 1/3 dx. All right, so this is one of those things you just kind of have to try, mess around, see if it works, a little intuition. And so this is ends up being a u substitution. So you pick this to be u, and your du ends up being this. It works out real slick. Okay, so doesn't always. These could be real messy. So let u equal x to the 2/3 plus 4. Then my du is 2/3 x, and then you subtract 1 and you get negative 1/3, which is sitting right there, dx. So take a look at the highlight. So this x to the 1/3 dx is my u, or I'm sorry, my du, minus the integrating factor, of course. Okay, so they're right there. Factor being the constant that gets in there. So where am I? So what you get then is this. You say this is equal to the integral from 8 to 27, and that is actually x equals. We're not a u equals, so we'll keep it as x for now. And then that ends up being the square root of u, and then you bring that across, and that ends up, or multiply by the 3/2. So you end up with a 3/2 as your integrating factor right there. So this guy here has to get out of there, so you bring it over or something. There it is. Okay, let's highlight that. And then that's your du. All right, so now you integrate square root of u. I'll go ahead and bring out the 3/2. And then we just do this separately. This is 2/3 u to the 3/2 when you integrate the radical. And then this is still x equals 8 to x equals 27. You could convert this now to u and substitute, or you can substitute for u. It doesn't really matter, but I'm keeping track of what's what by putting that x there. So this is where you cannot substitute in for x equals 8 here. Okay, so we have to substitute back. That's what I usually like to do, by the way. So put a little note, substitute back for u. And you can do it either way. Or you may have been shown at some point you solve for u. So u is this, and then you solve for it. I don't generally like to do that because when you're trying to find a general form of something, you end up substituting back anyway. And so I like to keep that as a method, basically. All right, so substitute back, and you get 3/2 times 2/3, and then now what was your u? Your u is x to the 2/3 plus 4. So it's x to the 2/3 plus 4 raised to the 3/2. And you evaluate that from 8 to 27. All right, so then that equals, let's see, oh, the 2/3 can come out. So this is just 1. Let's do a little highlight here. Oops. So that constant comes out, and so that's just 1, right? So then you just get you get something messy, basically. So you get 27 squared plus 4 to the 3/2 minus 8, 2 squared plus 4 to the 3/2. I'll let you do the details on that one, but I get 13 to the 3/2 minus 8 to the 3/2. Okay, so make sure you get exact form. First. Okay, that's about as nice, exact as you want to get. You can't bring across the radical with the 2. It doesn't work that way. Right, that's an illegal math move. You can get an approximation to check it if you want. 24.2. This probably, you could integrate this back up. Ooh, I almost turned this off. Back up here. So if you plug this into Wolfram Alpha, you could probably get this. It would probably give you exact form of some sort. What was I going to tell you? It's not acceptable to go from here, like here to here, without showing all this work. So you need to show all that work. That's kind of the point in the class. Okay, so it's integrating, it's techniques of integration, solids of revolution. So you got to show how you get stuff. That's really the key here. You don't have to show like how you go from here to here necessarily. I probably would, but anyway. Okay, so that's pretty much it for arc length. I mean, you take your derivative, plug into the formula. You don't really do much else than that. But this derivation's, it's one of those things where I want you to study it. I'm not going to ask you about it, but if you really want deeper understanding of how things work, it isn't just formulas. It's how you derive it using these fundamental concepts of Riemann sum and all the past stuff we've learned. And so if you want a deeper understanding, that's what you need to do is try to see how this works and see when we do the next stuff, when I spend time on it, how to do it. Okay, moving on. Next is surface of revolution. There's a similar derivation that I am not going to go through. I am this time in 6.4 just going to give you the formula, and then we'll just apply. We'll do like one example. So I'm not going to spend a lot of time in surfaces of revolution, and then we'll get on to 6.5 a little later after that. Until next time, we'll see you then.